All right, so I wanted to finish up with a couple slides that we didn't get to today. Essentially, we were looking at the conditions for equilibrium, but we got into the three-dimensional situation. The examples we worked on in class were just 2D examples, which made it a little easier. If we have a three-dimensional situation, we actually end up with 6 equations for equilibrium because of the fact that we now have the possibility of having moments in all 3 directions, where in 2 dimensions we only had a moment possible about one of the axes. We also, of course, will add the additional equilibrium condition in the z direction for the forces. So as you can see, we have 6 equations, which means we can have up to 6 unknowns. This could make something rather complicated, but I wanted to talk about, an example to just show how we might simplify it. So we have this scenario of this assembly, and we want to figure out, we're actually trying to figure out the reactions at the bearing and also the force that's in the cable that goes from B to C. Now, if I was going to label these reaction forces at the bearing, remember what I have to think about are what are the directions of motion that aren't being allowed. And so I can see that there will not be any motion in the z direction allowed, or in the x direction won't be allowed either. It actually could move along the y-axis, so there's not a support reaction in that direction. Similarly, there could be rotation about the y-axis, but there cannot be rotation about the z-axis or around the x-axis. So I have 4 different support reactions that I have in this situation. I also have a load that is acting at point D, and I also have this tension in the cable that goes from B to C. Now, as I'm thinking about my equations for equilibrium, I would obviously have the equations in the x direction equals 0, in the y directions equals 0, and in the z directions equals 0. And I'm going to come back to that in a later slide. Now you might be wondering how we get the moments in the x direction and in the y direction and in the z direction, which all of these have to be 0. The idea would be that we would think of our forces, and our total moments would be the radius vector. We would have to choose a point of rotation crossed with the force, and this is going to present us with a matrix, which then is going to have an x component, that would be the mx, a y component, which would be the my, and the z component, which would be the mz. So the idea, what I'm trying to show here, is that whatever we would end up finding for these different components would represent the components of the moments, and it would be those expressions that we would set equal to 0. And so in this particular problem, it seems like this could be rather complicated because we have 2 forces and they're located at 2 different distances. So for instance, we might say, I want to use a different color just to make it a little more obvious. If we call this F1, we might want to draw a radius vector from point A to that. And so we would have M1 would be R cross with F1, and I really should number that and call that R1. And then I could also have another scenario, another contribution, because I would have R2, and we would say, that would be the radius vector that goes to the cable, and so M2 would be equal to R2, cross with F2. And so the total moment in this problem would be M1 plus M2, which we could be finding using the matrix form and going through all that work. That's an incredible amount of work. But it turns out that because of the nature of this problem, we can actually simplify it, and in this scenario, we actually don't have to do the matrix approximation or the matrix approach to finding the moments. You might be thinking, what the heck is she talking about? So let's take a look at this. Okay, so again, now we're just going to be presented with the problem, and we're going to go about it, solving it in a little bit of a simpler fashion because it works out pretty nicely. So we have this rod. It's supported by the thrust bearing and the cable, and there's a 80-pound force that is also a load on it, and we're trying to find the reactions at A and the cable force. So let's go back to our picture. We're actually going to redo it. And so we had said we had AZ and AX, and we had also MZ, and we also had MX. And so those were our reaction forces. Oh, I should have also indicated this was FBC. So these are the forces we're dealing with. Let's look at our equations for equilibrium in our three directions. So in terms of x components of forces, we only have AX. So it turns out that that one support reaction is 0. In the y direction, our forces are nothing. And in the z direction, there's a little bit more going on. We have AZ minus 80 plus FBC equals 0. Now, so those are two equations that we got so far from our conditions of equilibrium. Now, what I said was I don't have to do the radius cross with the force in this particular situation. I actually was able to figure out that you can find the moments about particular axes relatively easily. Remember that the moment about an axis, you are trying to figure out if I applied a force in the way that it's shown, like what kind of rotation might it cause potentially about each axis. So let's look at the sum of the moments around the x-axis. Now, what I'm trying to figure out is, for instance, for the 80-pound force and for the force of the cable, if the forces are applied in the direction shown, would there be a rotation about the x-axis, which is right over here? And then also, what would be the moment arm for that? And so when I'm looking at it from that point of view, I can see that, for instance, the 80-pound force, as it's pushing downward, would absolutely cause a rotation about the x-axis, and it would actually be in the clockwise direction. So I would have minus 80 pounds, and that force is actually 6 feet from the x-axis, and so that's the moment arm. I also have the force BC. Now that's in the opposite direction. That's going to cause a counterclockwise rotation, which makes it positive, and that moment arm is, of course, also 6. And then finally, we noticed that I had the support reaction around the x-axis that was that moment, because the thrust bearing prevents rotation about the x-axis, and the way that I drew that was giving it a counterclockwise rotation, and so I'm going to make that positive. And so that becomes one of my equations for the moments about the x-axis. Notice I did all of this pretty easily. Again, I'm somewhat lucky in the setup of this problem that it is possible. when I look at moments about the y-axis, now I have to think about, would any of these forces cause moments around the y-axis? And in this case, the 80-pound force and the force of BC, once again, actually would cause rotation about the y-axis, because now I'm looking at it from a different point of view. The 80-pound force actually would cause a clockwise rotation. That's if I'm looking at the axis from, basically I'm looking right here. And so as I look at it, it's causing a clockwise rotation. The distance is 1.5 feet. But again, BC is, the force BC is in the opposite sense. And so it causes a counterclockwise rotation, which is positive. It's 3 feet away. And I didn't have any support moments for the y-axis because the thrust bearing actually does allow rotation about the y-axis. And so these two things add together to equal 0. This actually gives me a way to calculate the force in that cable. And I find that it's 40 pounds. This is actually going to allow me to solve for some other things as I look. And just for completion's sake, I want to look at the moments possible around the z-axis. And so I do have that support moment around the z-axis, which again was counterclockwise. But notice that the forces, the 80-pound force and the force in the cable, can't actually cause any rotation about the z-axis, so I don't have any additional terms, and so that is 0. Now, once I know this, I can go back into some of these other expressions to solve for some other quantities. For instance, you can say AZ is equal to 80 minus FBC, so it's equal to 80 minus 40, so AZ is also 40 pounds. And then also, I can go back and calculate MX is equal to 80 times 6 minus FBC times 6. So this is 480 minus 240, which is equal to 240 pounds times feet. And that's how we can solve this problem. I kind of liked how this one worked out nicely, even though it was 3D, and I hope you can follow it, but if you can't, just please ask some questions, either Zoom with me or ask me in class.